Okay, so we were talking yesterday about space curves, section 10.1, and you have an assignment next week on that, due on that next week. So let me give you a moment to copy this example down, okay? Okay, so in this problem, okay, we have this space curve. Okay, we have this space curve moving through space, and actually, well, this space curve is restricted to what plane? Based on the equation here, this space curve is restricted to what plane? Good, the XC plane, because you have, well, I mean, okay, hold on here. What's the J component? What's the component of J here? Well, not all. I appreciate all participation. So there's an I component, a K component. The J component has to be 0. Okay, J component has to be 0. Okay, are there any questions so far? Is everybody comfortable with that? All right, Ryan is. Diodath, are you comfortable? Thank you, name Francesca. Diodath, are you okay with that? Comfortable?
Yes.
Excellent, excellent. So this problem, when I looked at this problem, I think of a paraboloid. Okay, I think of a paraboloid. The fact that the curve is it's a space curve restricted to the XC plane doesn't really change how I'm going to approach this. I know what a paraboloid looks like, and this is the paraboloid that I have. And I know there's a space curve, okay? I know there's a space curve, and the space curve is going to intersect the paraboloid. It's going to intersect it. It's going to go in and maybe go out of the space. The space curve will, intersect the paraboloid at a point, and it'll exit the paraboloid at a point because the space curve keeps going, right? Space curve keeps going. So maybe this space curve intersects the paraboloid in two points. So this is kind of, what I think about when I do this problem. And so for the solution, what I did, I'm not saying this picture's like correct that I'm drawing here. I'm not saying this picture is correct. But I guess all I've done. Well, actually, hold on. I take that back. The space curve is restrained to the XZ plane, so I've drawn a space curve, and let's just assume this my space curve here stays in the XZ plane. Okay, no problem. It's going to intersect the paraboloid and exit the paraboloid, and we want to know what times that occurs. If I'm going to find the points of intersection between this space curve and the paraboloid, the first thing I need to know is what times does the space curve intersect, like enter the paraboloid, and then what time does the space curve exit the paraboloid? So that means we need to find times t, okay, times t such that z equals x squared plus y squared. I mean, what we're saying is and I think it's sort of clear there's going to be two answers, two time values for which the paraboloid intersects, for which the space curve intersects the paraboloid. Okay, one time upon entering the paraboloid and another time upon exiting the paraboloid. But at the points of intersection, the x and z components of the space curve have to obey the paraboloid. And the paraboloid says that z equals x squared plus y squared. So to find the times, to find the times of entry and exit, I take the z component of the space curve, okay, and set it equal to the sum of the x component squared plus the y component squared. See how I did that? And then that allows me to solve for t. That allows me to solve for t. Okay, are there any questions on this part here? Okay, well, if you're good with that, then I go ahead and 2t minus t squared equals t squared. I'm going to solve for t squared. I'm not going to divide by the variable t because that'll eliminate one of my answers. You know not to do that. You'll get t equals 1 and t equals 0. And that means when t equals 0, okay, when t equals 0, this here, the point 0, 0, 0 stands for the space curve vector at time equals 0. And 1, 0, 1, and all you do is you substitute in t equals 0 in the space curve here. When t equals 1, okay, when t equals 1, the position vector of the space curve after 1 minute or 1 second is going to be 1, 0, 1. Again, just substitute t equals 1 in here. And that's how you get that answer. Okay, are there any questions? Are there any questions on this particular problem? Okay, all right. All right, so I'm just you're gonna let me know when you feel you've come when you've had enough time to copy down the problem. Okay, great, great. Well, now what I'm going to do, I want to actually look at a problem from your textbook. Okay, so let me go into WebAssign here, and let me see. I think I have to log back in. One moment. I'm going to bring up the ebook. One moment here. Okay, I gotta. Okay, I'm getting it here. Should probably, let's see here. All right, so vector functions, that's what we're in. I want to look at example 6 with you. So let me find example 6 here. Okay, stop there. Okay, so here, the intersection of two surfaces is a space curve. Okay, so in this problem, example 6, we have, well, I mean the problem says find a vector function that represents the curve of intersection of a cylinder and the plane y plus z equals 2. Okay, so in the figure here below, well, let me ask you this. Because like y plus z equals 2, that plane, that we know, I mean, is the plane y plus z equals 2, is that a vertical or a horizontal plane? In other words, here, I'll show you what I mean. So you have a plane. Y plus z equals 2. And we could write that as z equals 2 minus y. Okay? So if I draw a y and z axis, okay, so I'm in the plane of the whiteboard, I'm drawing a y and z axis, and the x-axis is coming like directly at you. Okay, well, z equals 2 minus y. If we were to graph that, okay, we would have, I mean, I'll show you what I'm really doing here. So this is z. Hold on here. The y-intercept is 2. The slope is -1. I mean, if I were just saying like let's talk about just a line. Let's say I had a line, z equals 2 minus y. I draw a YZ plane, and this is what the line looks like, right? It has a y-intercept of 2 and a slope of -1. Ryan, do you question on that?
No.
You're comfortable. Okay.
Yeah.
Okay. Ryan, by the way, just so I don't forget, I noticed you had sent me an email earlier. I didn't have a chance to read it, but we can talk about that. We can talk about that if you want to chat after class about that.
Sorry,
about
Professor. That wasn't
Okay.
me. I think that's the other Ryan.
Oh, that's the other Ryan. Okay, the other Ryan. Okay, sorry. Okay, right. Yeah, we have 2 Ryans in here. That's right. Okay, no problem. Okay, so now, you know, you can see how the line's oriented. So say now in 3 dimensions, you have an x-axis coming out at you. Think about what the plane would look like. The plane would have to, every cross section of the plane would have to have this as a line, right? Just take that line, and move it along. Well, I got to be a little bit careful, but you move it along the x-axis, and you get a plane. And so when we go to the picture here in the ebook, is it? Hold on here. Does that picture in figure 5 make sense to you? How the plane is cutting the cylinder and why it's cutting it at that angle. Okay, Diadath is comfortable. Good. Did that help, that little picture I drew on the whiteboard? Did that help? You sort of, okay, excellent, excellent. Good, good, good. Tricks of the trade, tricks of the trade, right? Okay, so great. Well, now we have a space curve. If we look at the intersection between those two surfaces, the plane and the vertical cylinder, we get a space curve. Okay. So we want to find what the equations are for that space curve. We want to find what the equations are, what the parametric equations are for the space curve. Now, what does hold on here. Okay, so Eric's saying it's a cross section of a cylinder makes a circle. That's exactly right. The space curve has to, since the space curve lies on the cylinder, it has to, the x and y components of the space curve have to obey the equation x squared plus y squared equals 1. So if you had to, so since the x and y components of this space curve have to obey x squared plus y squared equals 1, can you tell me what you think x would be, and what you think the parametric equations would be for x and y, given that there's spiraling going on here? Think about taking that space curve, and if you were to take that space curve in figure 6, every coordinate on the space curve, every point on the space curve has an x, y, z coordinate. But if you were to take the space curve and project it down into the xy plane, what would you have if you projected that space curve down into the xy plane? What would you have? What would the projection look like of the space curve in the xy plane? A circle. That's right, Ryan. It would have to be a circle. Okay, so a circle that whose x and y coordinates obey x squared plus y squared equals 1. So can we make the jump here and say that x has to equal cosine of t and y has to equal sine of t for that space curve? I mean, is that hold on here. Did I lose the hold on, let me bring the book back. I think I lost the book. Hold on. Hold on here. Okay. Can we go from saying, okay, here's the space curve, that's the intersection of the plane and that cylinder, to saying that the x and y components of the space curve have to be, or the parametric equations for x and y have to be cosine of t and sine of t? Can we say that? Are you, Ryan's okay with that? All right. Is anybody, it makes sense? Eric says it makes sense. Okay, good, good. Deodath and Robin are comfortable. Good, good. So, okay. Now, what's left? What parametric equation's missing? Good, that's right, Ryan, the z. Because this space curve here, this space curve is, every point on that space curve has some z coordinate, and the z coordinate isn't equal to 0, it changes. Well, how are we, what's going to dictate how we get how we get the parametric equation for z. What do we need to now? What do we need now to consider? What haven't we considered yet? We considered the cylinder. We considered the cylinder, the projection of C onto the XY plane was that circle, and okay, but what haven't we considered? Hold on. The plane, that's right. Now the plane, as you know, is z equals 2 minus y. Well, since y is the sine of t, okay, z is going to have to equal 2 minus the sine of t. And this allows us then to write we have our parametric equations for this space curve. We've parameterized the space curve. Okay, are there any questions on that? Okay, Deodath is comfortable. Good, good, good. All right. Let me just let me see here. One moment, class. Okay. Well, I'll tell you what, let's look at another example. If you're good with this, let me bring up another example here. Let me find it here on my thing here. One moment, I gotta find it. I want to look at one more example here if we can. Last time in class, by the way, we learned how to graph space curves using MATLAB. So we learned how to do that. Okay, so let me bring this up here. Okay, I want to do another example with you. Okay, let me give you a moment to copy this example down, because I think in section 10.1 homework, I think these kind of problems are going to give you the most difficulty. Okay, all right. But I like them because you have to it really forces you to visualize things. So take a moment to copy it down. Very good. Okay, so here we want to find a vector function that represents the curve of intersection of this semi-ellipsoid. It's semi-ellipsoid because y is required to be greater than or equal to 0. And then there's this cylinder. Let me ask you, this cylinder here, x squared plus z squared equals 1, is that an up and down cylinder, or is it a sideways cylinder? X squared plus z squared equals 1. Good, it's sideways. What's the axis that goes through this cylinder? The x-axis, the y-axis, or the z-axis? Good, the y-axis. Good. So very good. So what I want to do, I want to bring up I made a little picture. So I'll go to the next page if I may. Does everybody have the example copied down okay? Okay. All right. So, okay, what I did was I drew this ellipsoid. Okay, well, let me use. So an ellipsoid looks like a football, but this is a semi-ellipsoid. So what you can do, remember, a semi-ellipsoid, you can put it in standard form. You can put it in standard form, and that goes. If you look in section 9.6, the second table there, it gives the standard forms of different quadric surfaces, and this is in standard form. So the x-intercept is here. Well, what I mean is the 4 below the x squared means the x-intercept is plus or minus 2. The 4 under the y squared means the y-intercept of this ellipsoid is plus or minus 2. And the 1 under the z squared means the z-intercept of this ellipsoid is plus or minus 2. So, I mean, to make the sketch, that's how I came up with the sketch. So here's like this highlight here. What intercept is that I'm shading? What intercept is that? Is that the x-intercept, the y-intercept, or the z-intercept? That yellow shading there. Y-intercept, good. Oh yeah, that's a 2, okay. What's this intercept here? Is that an x, y, or z intercept? That's an x-intercept. Yep, plus or minus 2, so I got it here and here, very good. And then finally, the z-intercept is plus or minus 1. So you see, basically, by determining the intercepts, I'm able to draw that ellipsoid. Let me give you a moment to catch up, okay? Okay, so now we for our solution here, this is the solution. I have an ellipsoid, and the cylinder, this cylinder is a sideways cylinder. The cylinder x squared plus y squared plus z squared is a sideways cylinder. And the sideways cylinder, see, I don't want to draw too much, on my picture, but in my mind, I can picture this sideways cylinder who's what was the cylinder, the equation? Hold on, the cylinder. Okay, the cylinder had equation x squared plus z squared equals 1. So that cylinder is going to intersect the paraboloid certainly here. It's a cylinder of radius 1 that moves along the x-axis. So it's gonna hit the paraboloid, the ellipsoid there and there, and then let's see. Want to be a little bit careful. It's gonna trace out a space curve on the ellipsoid. Okay, it's going to trace out a space curve on the ellipsoid. Well, I want to be, yeah, it will. But the question is, what is that space curve? Well, all right, we know that because now for the intersection, we have the intersection of this cylinder here and this ellipsoid. So that means where the intersection is, both equations have to be true. The components, the x, y, z, the x, y, and z components of the space curve have to obey both the cylinder and the ellipsoid. Well, if the space curve is going to obey the cylinder, then you're going to need that for this space curve, the x component is the cosine of t and the z component is the sine of t. You're going to need that, right? So you determine two components of your space curve right away based on the fact that where the space curve or where the cylinder intersects the ellipsoid, that curve of intersection has to obey the equation for the cylinder. And the only way that would happen is if x is cosine of t and y and z is sine of t, because only those two parametric equations would give you x squared plus z squared equals 1. The question is now, what's missing? What's missing? What parametric equation is missing here? The y. So how are we going to get, that's right, Ryan, how are we going to get the parametric equation for y? What haven't we used yet in the problem? What haven't we used? We've used the cylinder. We've used that equation. Now we got to use the semi-ellipsoid equation. Okay, so, well, the semi-ellipsoid equation is x squared plus y squared plus 4z squared equals 4. So I'm going to solve that for y because I'm looking for y equals something, right? Well, I have y squared equals 4 minus x squared minus 4z squared. That's fine. Okay. And you know, these are just really little mental notes on the right here. You don't need to really worry about that. But hey, when I take the square root over here, I have a plus. Why is there a plus? I thought when I took the square root, I would get a plus or minus. Square root of 4 minus x squared minus 4z squared. Why do I have just a plus there? Because y is greater than 0. We're only concerned about, good, Robin, about the right-hand portion of the ellipsoid. So that means then now I know what y is, and I'm going to substitute for x and z the parametric equations for x and z. Okay, and so I mean this is fine what I have here, but I want to simplify that a little bit. Sine squared is 1 minus cosine squared, and so I end up with the square root of 3 cosine squared of t. That's just going to be square root of 3 times the absolute value of the cosine of t. And then this gets me now my space curve. This is the kind of thinking, you know, that section 10.1 will teach you. Okay, take a moment to copy down a moment here. Okay, are there any questions on this problem? Okay, how many found this? I was debating about whether to do this second example. How many of you found that second example to be helpful? Okay, good, good. All right, I'm glad to hear it, glad to hear it. Thank you, everyone. All right, what I'm going to do, I'm going to stop there, and I'm going to give you a little time to work on your section 10.1 exercises. So I'll deactivate the others because I want you to focus on 10.1. I think I can maybe give you 15 or 20 minutes to work on your 10.1 exercises. So let me stop the recording. Are there any questions at all? Okay, I'll stop the recording.